Sí, ya voy. ¿Ya? ¿No van a cerrar la puerta? La puerta. No, no. La puerta. Buenas tardes y bienvenidos al 9º Simposio Internacional de Física, Crónicas del Futuro. Continuando con nuestro ciclo de conferencias, presentaremos a la ingeniera Anna McGowan. Before introducing Dr. Anna McGowan, I'll give you a brief introduction of his work. Ana Maria Rivas McGowan has a bachelor's degree in aeronautical and astronautical engineering from Purdue University and a master's degree in aerospace engineering from Old Dominion University. Mrs. McGowan has over 14 years' experience in aerospace engineering and technology development. Currently, she is the Chief Technologist for External Business for NASA Langley's Aeronautics Research Directorate. In this role, she leads the development of external collaborations and business development for aeronautics. She also serves as the Defense Advanced Research Projects Agency's agent on their Morphing aircraft system program. She has developed, planned, and managed projects in the areas of innovative high-lift technology, aeroelastic technologies for regional and supersonic jets, extreme short takeoff and landing, tailored lightweight wing concepts, morphing airplane concepts and technologies, microflow control, adaptive materials and structures, and biologically inspired flight. These projects include several partnerships where Ms. McGowan cultivates and enhances key strategic collaborations with other government agencies, industry, and academia. In 2004, she completed her 5-year tenure as a manager of NASA's Morphing project. This visionary $35 million per year project involved over 90 researchers and 20 universities in developing and assessing advanced technologies to enable efficient multi-point adaptability in the future flight vehicles. Now I'm pleased to introduce to you all Engineer Anna McGowan, who will be giving a lecture on Technologies for Adaptive and Morphing Aircraft.
So thank you for the introduction, and thanks for welcoming me here in Monterrey. It's my first time here, and it's been fun. It's been 3 days, and I've had a chance to meet a lot of the students, and everyone has asked me, how do you like Monterrey? And what's most interesting to me isn't the city, but it's really the students. So thank you guys for being so hospitable to me, all of the students and the professors. So I'm going to give you a short presentation, not really short, on technologies for adaptive and morphing airplanes. And I'm sure many of you said, morphing airplanes, is she crazy? The answer is yes. But what I'm going to try to do is remove some of the mystery around morphing aircraft, remove some of it, and explain other parts of it. We've been working in this area I've been working at it almost my entire career. And it's been a lot of fun. What I'm going to do to explain it is start with some history about morphing aircraft, because it's not completely brand new. Some of the challenges from what we have done, we have tried a lot of different technologies. Some have worked, some have not. And then I'll describe some lessons learned from our own failures at NASA and successes as well. What I'm going to do is first hop out and show you 2 quick videos, and just to make it a little more interesting. The first video that I'm going to show you is one that we created at NASA Langley. And we were asked by the NASA administrator to dream. What could you do if you could make airplanes do anything you wanted them to do? So we started with looking at birds, and we dreamt. This was meant to be a cartoon. It's not a real airplane, but with an animator, an aerodynamicist, and a structures person, we dreamt this airplane, literally around the small coffee table in my office. And our idea was an airplane that wings could sweep back when you wanted to fly fast. On the wings would have tiny jets that would control the flow. On the back end would be small little flaps instead of big ones, similar to feathers. The wings would come forward when you wanted to move more slowly. And then like a bird, you would flare the tip feathers when you wanted to turn. Even inside this wing, our envisionment of the future is instead of having normal rods of metal, it would be more like muscle tissue pulling in together. And on landing again, you'll notice the wings curve, again, very similar to a bird's wings, and the tips flare as well. This was completely a dream. It was not something that existed in some book somewhere, and it was fun to have the opportunity. What we did not expect was for this to end up on the House Senate floor at all, on CNN, on the internet, and now all over the world. So you never know what you can do by dreaming. It started off as just a crazy idea, and now it's been everywhere. So that was one of our dreams, and I will show you another one. When we actually do develop the technology, many folks ask, well, how do you get there? Of course, you can't go immediately to that. It takes decades, 20, 30, 40 years. This is a wind tunnel test. This is a wind tunnel that I worked in for 10 years. It's called the Transonic Dynamics Tunnel, and this was one of my last wind tunnel tests. This was a model of an unmanned air vehicle. We did this with DARPA, the Air Force, and Northrop Grumman. This wing that you see here, the idea was to make it smooth. There are no breaks in it except at the very beginning and the end. In between, it's completely smooth, and you can make any shape that you want. So the idea is to, again, think about birds. They have a very smooth edge on their wings. They don't have a flap like you see on airplanes today. And so we built this wing with Northrop Grumman and the Air Force and DARPA, like I mentioned, and we tried many different shapes to define, hey, now we can make any shape we want on the wing. What shape do you really want? What is best for what Mach numbers and speeds? And so these are 20 different shapes that this wing could create. Now you notice the main part of the wing is staying still, and it's just the trailing edge that is changing shapes, and that is often the most important part of the wing to change shape. So this was a pretty revolutionary step for us, all of us that are working in this area, to see what is possible when you can morph even just a part of the airplane wing. So, and this particular structure was made of a rubbery-like material on top and very smooth inside. So now, how do you go from that to actually morphing airplanes? One idea is kind of a dream, and the other idea was a wind tunnel test. What happens in between? Before I get there, I wanted to show you some acknowledgments. I do this every time I do a presentation because I think for students especially, when you see a speaker, you assume that, wow, they've done all this work. Allie just read an introduction that makes me sound like I'm great, and I'm really not. The only thing that's great about me are the people that I work with. They are fantastic. I work with a great team of researchers and scientists at NASA Langley that make me look great, honestly. My core team is up there: Lucas, Jamshid, Jim, Tony, Terry, and Jeff. And then also over 100 researchers that are very much like you guys in 10 years. I'm at NASA Langley. We work with NASA Dryden, NASA Glenn, DARPA, the Air Force, the Navy, the Army. We also work with the industry, Lockheed Martin, Boeing, Northrop Grumman, many companies that you know. Universities, over 30 different universities in the United States that we work with. And even internationally, I have several colleagues that I communicate with regularly. And I do that to tell you that when you have student projects where your professors force you to work with other students, there's a reason for that. It's because in order to do anything great, you will likely not do it by yourself. You're going to do it working with someone else. And so this is my team. So what I'm going to talk about here, first I will start with where I work, NASA Langley. Everyone has asked me, so you are from Houston. Houston what? I'm from NASA Langley. We're much better. So I will give you a little bit of background on where I work at NASA Langley, and then I'll describe what is morphing, why would you do it, and then give you a little bit of a history lesson on airplanes. Many of you are thinking about astronautics, I realize. But as we often say, the first A in NASA is aeronautics, right? It came before space. So then I will talk about morphing today, some of the challenges and lessons learned, and then morphing for the aliens. You'll just have to guess what that is. So first, NASA installations. We are everywhere. There are 9 NASA centers, plus 10 including the Jet Propulsion Laboratory in California. JPL is out here. We're over here at NASA Langley. We're about 2.5 or 3 hours south of Washington, D.C. Other NASA centers, just for you to be aware of, you're familiar, of course, with NASA Johnson in Houston, NASA Kennedy. The Stennis Space Center is where the rockets and the engines for the space shuttle are developed, believe it or not. NASA Marshall Space Flight Center develops a lot of the technologies that are going into what's launched from Kennedy. NASA Glenn does propulsion technology, jet propulsion technology. Many of you are talking about energy. Those guys are the ones that are leading some of our energy work. NASA Ames is a large computational facility, and also NASA Dryden Flight Center is where we fly our large experimental aircraft. And it really does take all 9 NASA centers to create what you guys see as NASA. So let me get to the best NASA center, only slightly biased. The best NASA center, only half joking, was founded in 1917. And you probably remember when the Wright brothers flew, I hope, 1903. 14 years later, the US government started the first civil aeronautical research laboratory at Langley Field. Believe it or not, it's hard for me to believe. Before the First World War, also. Rather interesting. This is where NASA started, was at Langley. The buildings are extremely, extremely old. We always complain about that. The amount of money coming into Langley is about $610 million a year. Most of that's from NASA. We also have external business. At the center, there's about 3,500 people that work there. Roughly 2,000 are what we call civil servants. Those are people that are actually federal employees that work for NASA, like myself. The other 1,500 are contractors. Many of you have asked me, do you have to be a US citizen to work at NASA? And the answer is yes, if you're going to be a federal employee. However, our contractors come from all over the world. Infrastructure. NASA Langley is quite large. It's almost 800 acres, 240 buildings. And we were always asked, well, what if you had to replace this whole place? What would it cost? And a rough guess is about $2.7 billion if you had to replace the center. And just for reference, my office is right there. So, how do we spend $610 million in 1 year? Well, the biggest part, by the way, just goes to keeping the door open. We call it institutional support. We have many laboratories and facilities. Your professors can tell you how much it costs to keep our laboratory open. Well, it costs us about $250 million or $250 million a year to keep our laboratories open and operating. We also do a lot. Aeronautics, as you can see, is our biggest part of what we do. It's $158 million. We do exploration. We help with work on the space shuttle as well and other entry vehicles. We do science work, space operations, and we do a lot of education programs. One of the reasons I'm here, of course. So what happens at NASA Langley? We do aerosciences, which is research in all atmospheres. We do from the ground to space, space shuttle, planetary vehicles. We also do what's called systems analysis. Much of this looks like cartoons, but it is our way of dreaming. How do you look at the entire system, an entire Mars architect, an entire moon landing from beginning to end? Most times in your career, you're going to end up looking at just one component, the tire or the wing or just one vehicle. What we can do with our simulation capabilities is look at the entire thing, how the Mars airplane will fly over Mars, where it's going to land, etc. We also do cloud research, believe it or not. We characterize all atmospheres. We launch balloons that go over 100,000 feet in and take cloud measurements, and then structures and materials. I'm going to show you a couple of these very briefly. So aerosciences. Again, many of you have asked me, what are some parts of aeronautics? And here are just some examples. And this includes the things that we do at NASA Langley. Aerodynamics. We have several different wind tunnels. I'll show you several of them. But we do computational fluid dynamics to analyze the flow over all types of vehicles. Acoustics is the study of noise. You might be wondering, why would NASA be interested in noise? Well, noisy things don't fly typically very well. But we have a really good acoustics facility. Aerothermodynamics. Many of you have thermodynamics, heat and mass transfer. Aerothermodynamics is a thermodynamics you get from the air rushing over the airplane. It affects everything in how the airplane performs. If you think of a space shuttle, it is so hot when it's coming in and so cold during other parts of its flight that unless you understand the aerothermodynamics of its entire flight, you will not model the airplane or the space shuttle correctly. So that's a big part of what we do. We also do flight dynamics, guidance, and control. What this means is flight dynamics is how the airplane actually moves in space and how you guide it in for a landing, for example. And then we have really cool simulators. The simulators are big, huge globes, and you sit in the middle like you're in a cockpit, and it's like you are flying. There are clouds around and even other airplanes, and you can fly the airplane just like you were in the actual airplane. My first time was I was in an F-18, simulated F-18. There was an F-18 pilot next to me, and he killed me 10 times in about 5 minutes. It's really embarrassing. And I'm leaning on the stick with all my body weight, and he's So these are really neat. We use these things to model new avionics systems. We can tell if you have a new idea or concept for the cockpit, if you will. We can simulate that, put a pilot in there, and he can fly it and tell you, hey, this is going to work, this is not. We can do this before we have to put an airplane in the sky with a human aboard, which is much more unsafe, of course. And the systems engineering is how we build and make things. We build a lot of models and test them, a whole bunch, which makes our job a lot of fun. So, more. Aerospace structures and materials concepts. A lot of NASA Langley does materials development. And this includes stuff like, I call this our mad scientist laboratories. These are physicists and chemists that have all things of bubbling and little test tubes and things. They basically can create any material that you want. And I will show you some of the materials that they make from scratch. It's really kind of cool. You have a chance to dream and say, what if a material can do this? And our chemists will literally buy the raw materials in elementary form, mix them together, and cook them and make the actual. They don't like it when I call them cooks, but you know, that's what it looks like to me. Anyway, let's see. This is the wind tunnel I just showed you. We do aerodynamic testing. We also do, this is a large wing. We build large wings and we break them on purpose. It's kind of fun to get paid to break something. This is also a huge laboratory where we do what's called durability testing. You take a piece of wing or a space shuttle tile and you want to treat it like it's gone through many flights. So we literally beat it to death. We stretch it and pound it and shake it and compress it. We have one machine that's as large as this room that can put 1 million pounds of force on something to see how much it can take. So many folks ask us, well, how do you know the space shuttle can take all these loads? And we say, because we built it and we tested it. We will actually put 1 million pounds on something, literally, not in the computer, literally, and smash it to pieces. And then we go, yep, we were right. And then we know. So, wind tunnels. So I told you about structures. Now this is the fluid mechanics side of it. At one time we had 22 wind tunnels at NASA Langley, but with budget cuts we're now down to 8. We can test down from very small, slow temperatures. Our highest speed wind tunnel goes to Mach 13, and that is 13 times the speed of sound. This is how we do space shuttle testing. And in fact, let's see, these are our facilities over here for the really high temperature hypersonic speeds, and also the aerothermodynamics complex. Many of you that are studying physics, this is exactly where you would work. All of our space shuttle testing is done there. Let's see, this National Transonic Facility, it's the only one like it in this country. We actually use liquid nitrogen instead of air in the facility so we can get exactly right temperatures and characteristics. So, now the aeronautics program at NASA, this is for NASA overall. Again, several of you have asked me, what is NASA doing in airplanes? I thought you were a space agency. Well, this is our aeronautics program for overall NASA. There are 3 main parts of it. One is the next generation air transportation system. Believe it or not, how we fly airplanes today will not be what happens when you all get to be doing what I'm doing. Airports will look completely different. Right now, the airports that we design, they were never designed to be as large as they are. We just kept adding on and adding on. It's not the best way to do it. If you could redo it from the beginning, you'd have a very different system, and you would fly the airplanes differently. The air is going to get more crowded, but with computers, we can handle that. So a big part of our work is looking at what we call airspace and air portal. And aviation safety, it's beyond what most people think. Some parts of this, vehicle health management, putting tiny sensors all over the airplane. Similar to your own human body, you have little nerves everywhere. You can tell if your toe is hurting or your knee is hurting. Similarly, on an airplane, you would like to know if any part of it is not operating. With new technology, we can put sensors all over the airplane and give the pilot complete information, just like a human body, of how it's operating. And then fundamental aeronautics. This is where we study all flight regimes from subsonic, which is very low speed, to hypersonic, which are speeds well beyond Mach 10. And so this is the area that I've worked in nearly my entire career. So now, we'll look at a small portion of this, morphing. What exactly is morphing? So this is the part where we dream just a tiny bit. For a lot of folks, it's shape change. But if you think about it, most airplanes have some shape change now. The airplane shape that you need at takeoff is completely different than the shape you need while you're cruising around. So these are 4 common examples of morphing today. The F-14 Tomcat, variable sweep wing. It lands on an aircraft carrier. But it also needs to fly past the speed of sound. The wings need to be swept back for high-speed flight. They need to be swept forward for low-speed flight. Landing on an aircraft carrier is one of the hardest places to land. The aircraft carrier is small. It's narrow. It's bumping up and down with the waves. The pilots have no room for error. They've got to be able to control the airplane very well. You can't do that if your wings are swept back and in high-speed conditions. If you watch a bird when they come in for landing, what do? The wings come up. Wings out like this means you have lots of low-speed control. And it's exactly what the F-14 does. Another obvious example is the flaps for takeoff and landing. Again, think of a bird. When the bird's coming in, it stretches its wings way out. Well, flaps deploy on an airplane that you've all seen, basically to stretch the airplane out, give you as much lift as possible. Retractable landing gear, kind of boring, but it's morphing. It's changing shape, right? Pretty straightforward. Variable incidence nose. On the Concorde, in the early Concords, they couldn't see when they were landing. The nose was so high up. So they had to put the nose down so they could see when they were coming in for a landing. So, what morphing is not is aliens and UFOs. I have been asked many, many, many times, am I helping the UFOs in Roswell? And the short answer is yes. And when we do this, we're actually not doing alien research, believe it or not, but a lot of folks ask me about UFOs and aliens. That's not what it is. Morphing is also not doing what we call airplane torture, doing really bad things to perfectly good airplanes. A lot of folks said, are you going to make the wings of a 747 flap? No. Am I going to put feathers on an F-18? No. We are not doing airplane torture. We are trying to be much more sensible about it. So, what actually is morphing? I'm going to start from the bottom. Morphing is about adaptability. Our idea, or our dream, was to make the airplane very versatile and very resilient so it can fly in a wide variety of flight conditions. We also wanted to do this at many different points, multi-point in the envelope. Fly fast and slow, high and low, carry lots of passengers and be narrow. So basically be able to do a lot of different things. But here's the thing, it has to be efficient. If it weighs a lot, if it takes a lot of energy, if it's really complex, it'll never work. So it's got to be efficient, multi-point adaptability. That's what we're really after. DARPA and AFRL have often called this, you need a state change if you're going to do this to an airplane. It is a dream, but we already do it today in a limited fashion. So, an early history of morphing airplanes. We were not the first people to think of this. In fact, much of the early work was inspired by nature. Early aviation. One of the first people to actually fly was a guy named Otto Lilienthal in Germany, 1889, believe it or not. Even some of your professors are not that old, believe it or not. But they're going to kill me. He wrote a book called Bird Flight as a Basis for Aviation, and this is actually Otto Lilienthal right there. He actually died flying his concept, believe it or not. But he made wings that were very similar to bird wings, as you can see. And look at how beautiful this is, and look at Otto's wings as well. The birds have an amazing range of motion. Many have erroneously said that the Wright brothers did not look at birds, and that is actually incorrect. They did, in fact, examine birds. Here's a quote from Orville Wright. Learning the secret of flight from a bird was a good deal like learning the secret of magic from a magician. After you know the trick and what to look for, you see things you did not notice when you didn't know what to look for. What he's referring to is they had a challenge with controlling the airplane. They could make these wings that had enough lift, but you would stumble and fall. You had to control it somehow. And how did birds do it? Birds use their tails, a little bit of backside. Tails get moving back and forth. If you watch a bird in landing, their tails are morphing like crazy. They're twisting and turning, they're flaring, they're coming in. The wings are twisting and turning as well. The Wright brothers had a patent on wing twist. And in fact, they had cables in their wings. It was attached to the guy flying. Literally, it was a cable from his body to the wings out here, and he would shift to one side to pull one wing down and shift to the other side. And what he was doing is bending and twisting the wings to control the airplane in flight. And then, voila, successful flight. So, now let's talk about other morphing concepts. I want you to look at the dates for some of these things. Gallaudet had a really great idea in 1914 of variable wing tips. 1950s, Goodyear had an inflatable airplane. Why the heck would you have an inflatable airplane? Well, let's suppose you're at war and you get stuck in enemy territory. You're screwed. That's not a technical term, but you understand. And you have to get out of there. So you blow up your airplane and you fly away. It actually worked. They actually flew this airplane in the 50s, believe it or not. You know, I'm thinking all you need is a slingshot, right? And the guy's down, right? But whatever. Anyway, 1952, the X-5. This was the first variable sweep airplane. The F-14 I showed you earlier was designed in the 1960s. This flew 1952. It took from 52 to 72 for the F-14 to be built, 20 years later, before we could convince ourselves that something as crazy as variable sweep actually works. A lot of students ask me, so when will morphing airplanes become a reality? So when we can start dreaming again. It's very risky, it's very new and novel. Many technologies take 20 years to come, even after we flew an airplane. Even the Vanessa Beach, 1969, had these wingtips that went down, and I'll show you a few others. So, this is the oblique wing, 1980 flight test out at NASA Dryden. The wings actually just turned like a pair of scissors in flight to help it go from high speed to low speed. Pretty weird, but it flew. Right now, DARPA is building another version of this exact concept. But in DARPA's case, they want the entire fuselage and everything to turn with it. This was another airplane, the XB-70 Valkyrie, still one of the largest supersonic airplanes in the world. The wings tips change considerably in flight. It's a big, huge beast. But it also flew 1964. And there's with the wing tips down in flight. Really nice bird. So, what's new? That's the old stuff. What have we done since then? In the early part of the 1990s and this current century was a huge increase in doing work in adaptive and smart materials. And this formed the basis of morphing concepts. So I know many of you are not familiar with smart materials. I'm going to start there. Morphing materials. Smart materials have formed the basis for morphing. It is what gave many of us our dreams about morphing. So what is a smart material? This is a good physics lesson for many of you, by the way. So pay attention. Your professors might quiz you. A smart material, a material that responds to a stimulus in a repeatable and controllable manner. Stimulus is usually electricity, magnetism, heat, or light. Okay, translation of that is most materials we call are dumb materials, like wood, right? It carries load or weight, that's all it does. A smart material, if you apply electricity, it'll move, believe it or not. It'll stretch, strain, or push on something. So the material has two functions. It can carry load, but it can also move and push things when you want it to. A really cool feature. And you can freak people out with this, by the way, really easily. So a smart structure, oops, let me go back. A smart structure is just a structure that actually uses smart materials. So you take the smart material and you embed them. We also use terms like multifunctional, intelligent, or adaptive materials and structures. So why would you use this? Very often they can simplify the mechanical systems. As an example, a plant in Germany that makes huge textiles like carpets. They had first many different little machines that were going back and forth to sew it. Every single needle had a little gear on it that needed oiling every day. Lots of maintenance and mechanical parts. Instead, they put in a smart material, and all they had to do was give it a little bit of electricity, and the little thing would move the needle itself. It completely simplified how they sew their carpets now, and there's no more oiling and greasing and that sort of thing. Other examples, you can get a lot more functionality from the same system. Instead of just carrying load, maybe you can make it a sensor. Maybe it'll move for you if you want. Diagnostics, address unforeseen problems. You know what? Think about this for a minute. If your wing could repair itself, how cool would that be, right? The materials have to be kind of smart to do that. So these are some of the things you can do with smart materials. So this is an example of a smart material. It's called a piezoelectric, a very commonly used material. It is, in fact, probably the material used in your cars for the airbag sensor. Why? Piezoelectric is lead zircon titanate, a mixture of those chemicals. Now, in the piezoelectric, if you apply an electric field to it, like shown here with the voltage, it will actually stretch. If you apply a negative voltage, it will contract. It goes back and forth. So how can you actually use that? Well, as a sensor for your airbags, if you squish the piezoelectric, it will also create a voltage. So for your airbag sensor, if your car is squished, this little device is squished, it produces electricity and sends a signal off to shoot your airbag off. And it works extremely well. So, how can you use them? Micro-positioners, inchworms, speakers. This little device here goes up and down like a little heartbeat. It's used in a lot of speakers. Vibration control. They are placed often in large panels to control vibration. Other type of smart material, and this one really wigs people out. You can buy this stuff off the internet, by the way, I gotta tell you. These are called electrorheological and magnetorheological fluids, ER or MR fluids. What's really cool about these fluids, at some point they're just liquid, a Newtonian fluid. And one of them responds to electricity and one to magnetism. So let's do the magnetic one. At zero magnetics, it's basically a fluid. You add a little bit, and it becomes a little bit stiffer. It's kind of viscous, like peanut butter, right? And then you add a lot of magnetism. It is hard as a rock. It's like cement. It's really cool. Prostheses joints use these. Car shock absorbers in Germany use these right now. The basic idea is sometimes while the car is moving around, you want it to be squishy, right? Other times, you want it to be stiff. This is the idea also of morphing. The classic shock absorber is just one large coil. So it's the same stiffness all the time, right? And you don't really want that. You want one ride for the city and then another ride for when you want to go fast. You can't do that if you have a dumb system that cannot adapt. If you have a smart system that can change its stiffness, you can get exactly what you're looking for on control. You just change a little switch. So the things you can do with smart materials are amazing. They really are. This is one summary of different smart materials that are out there. Terphenol D, shape memory alloys, piezoelectrics, and then I had conventional materials. You can do quite a lot with them and how they operate. So now to some examples of things we've done at NASA Langley. I mentioned before that we have material scientists. These are basically chemists. These chemists are in a laboratory and can do anything they want with a material. They can create new materials. So they took a pretty conventional material, it's called an elastomer, and they said carbon nanotubes, pretty strong. We want to make this material that's got some really good properties. We want to make it better. So they literally do what we call doping it. This is not drugs, but it's like doping something. They basically inject carbon nanotubes into this other material and mix it all together and recook it. They hate the term cooking, but you know what I mean. So basically, this graph is a picture of strain. So if you have this material, basically it will only bend so much. The more and more carbon nanotubes you inject into this thing, you dope into it, the more and more it can bend. So you're creating this bionic-like material. And you can control how much this material moves by how much you dope it. And this is exactly what they did. They do a little bit at first. This is strain. And a little bit more and a little bit more. They can get a whole lot better performance with just doping it with carbon nanotubes. And so we compared the new bionic material to others that are out there, and it actually has much better capabilities. It has really nice strain, but it requires much less electricity to get the bionic capability. So, another example. Flexible skins. When we dreamt of these morphing concepts, we said, well, how are you going to cover the airplane? You need some sort of flexible skin to make that happen. So we also have a large group of structures and materials people at NASA Langley, and they spent some time dreaming. These are some really flexible materials, and we put rods in them for stiffness in one direction. Kind of like your bones are in the middle of your flesh, same basic idea. And this is what this looks like on the side. You can make fat rods or skinny rods, and we tried several different ones to see which ones work. And just so you know, students, when you fail, it is okay. It's from our failures that we've learned the most. When we make some of these samples and they snap apart in the laboratory, we learn a lot, and so that's okay. It's a part of research. Other examples is how you cut the material. I know you guys have a water jet cutter here, I saw on Thursday. And by using the water jet cutters, we've created all sorts of different mesh. These meshes can bend, and you can make a very flexible but metallic skin that can go on the top of the aircraft. So another example, shape memory alloys. These materials, really cool, again, ordered on the internet. If you add heat to these materials, they will remember their shape. So if you stretch them out and then heat them up, they'll shrink right back to where they came to before. So one idea for these materials was to make what we call the little chevron, this little lip right here, and we wanted it to bend and curve like that. How could you use that? You can use them on an engine, and I'll explain this in just a minute. Before we got there, we did a lot of fundamental research. The fundamental research was building panels where we would take, graphite and fibers and mix them with shape memory alloys and do many tests on them. We did frequency tests and load tests just to understand what we had. After we understood it, then we started building applications. One application was this engine. One of the challenges with airplane engines, they're very, very noisy. We know that if you make these little teeth, these teeth we're calling chevrons, if you put them on the back of the engine, they'll make it quieter, right? So why haven't we already done this? Why aren't they flying around now? The problem is you only need the teeth when you're taking off and landing. Otherwise, you don't want them there. They use too much gasoline. Worse yet, you want the teeth to sort of come inward a little bit at takeoff and landing and then get out of the way when you're cruising around at high speed. Most airplanes, the commercial airplanes, cruise around Mach 0.8, Mach 0.9, very close to the speed of sound. So how do you do that? Well, this was an example of a success story. We did lab tests on a simple concept. Then, with a lot of people, Boeing, General Electric aircraft engines, Goodrich, NASA, and even Al Nippon Airlines, we actually took a real Boeing airplane, a 777. We put these chevrons, or teeth, on it, and they actually had smart materials in them, shape memory alloys, so they would bend in when you wanted and then get out of the way when you didn't want them. A very adaptive concept. And it flew and did a great job. And you will probably see future airplane with these. When you see teeth on them and someone says, do you know why they did that with the airplane? You can say, well, a lady from NASA told me. True story. Another example of piezoelectrics, another really fun success story. In our laboratory, we have physicists and chemists. The physicists and chemists came up with these really cool materials, radial field diaphragms, electrodes, and I can explain some of these to you guys offline. But we developed these materials, and within a matter of 5 or 6 years, they were used on helicopters, airplane tails, spacecraft tubes, telescope. This was a controlling vibration, bicycles, cars, and a bunch of this. This is on the launch pad at Kennedy, by the way. So it's really neat when you can go from a really neat idea in a laboratory all the way to something that's being used every day, even to fly space shuttles. This material can control vibration on many different types. So it's neat to see it develop. So with this in mind, we dreamt about what you could do with morphing. So if you have these materials that can change shape, that can control vibration, that can sense things, how could you do it? What could you do with this? Well, our first idea was kind of silly, I'll be honest with you. We laugh about this thing. We call it the purple monster. But it was really us just sitting down and dreaming back in 1998. How the morphing project started, about 6 to 8 of us were in a room, and we said, let's put together an idea. In this room, we had a chemist, we had a structural engineer, who was me, we had an aerodynamicist, or we actually had a fluid mechanics person, a controls person, and probably someone I'm forgetting. Anyway, this was our dream. Maybe you could put sensors all over it to tell where the air was rushing over the wings. And you could have little jets puffing up and down like little feathers to control it. Sounds kind of crazy. And this picture is going to have me going like this, by the way. I don't know how you're going to explain that. We talked about having self-healing material, so if the airplane gets hit, it'll heal all by itself. And then also having shape memory alloy tendons on the wing to turn it. Sounds really crazy. What's even more crazy is that I got a call from my colleague in Germany, and he said, Anna, have you seen this? I said, no. And I don't read any German, so I'm kind of looking at this like, why did he send this to me? Well, I couldn't read anything except the words Anna McGowan. And I went, oh my gosh. Anyway, it turns out I'm promising to build this airplane by January 2021. So you can call me back then. But so a simple idea that we thought was just a funny concept ended up in a German newspaper, believe it or not. So be careful what you dream. So the NASA Morphing project. We did it for about 8 years. This is a really brief summary. Our focus was on developing the technologies, not the actual morphing vehicle. You first have to start, and I will show you how you start with an idea. We have a dream of a morphing airplane, but you have to figure out the bionic components that go in it first. And that was what we were focused on. And so we did adaptive structures and materials, unsteady flow control, advanced control concepts, and even biologically inspired concepts. We built pieces of wings, we tested other parts of them, new materials. This is a part of, I think, a seagull wing that we tested. We did a lot of reports. We worked with NASA Dryden and other government agencies and a lot of universities to do it. A lot of fun. So, back to morphing. This was our dream, efficient multi-point adaptability. And we really had to think of how do we get there, and when does it make sense? So, we're down here. We have these really neat materials, and we had to ask ourselves, could we make a morphing mechanism? Something like a wing or an arm that could move, like a bionic arm. But that's still not good enough. The next step is an overall vehicle component, like a wing, that's going to change shape. And then the last one is the actual airplane that flies around. So I made this for you all to see that there is a process from going from basic idea, building all the way up to the actual mission that you're going to fly. And how you actually develop your requirements, though, is the other direction. First, you understand what you want to fly. Someone asked me earlier in this symposium, you know, how do you decide what morphing technology to use? Well, we start with the mission. We're trying to fly fast or slow, high or low, big airplane or small airplane. You don't want to flap the wings of a large airplane, for example. So you start with the mission, you go down to the vehicle requirements, and then you go down to components and mechanisms and actuators. And this is how you break it down. You break it down this way, you test it back up this way. We call it the systems V. It's a common way of doing research. So, it starts with the mission, but often you start at the very bottom of that to work in. So the cost of shape change. One thing that we learned is that shape change doesn't always make sense. I'll explain this in just a minute, but let me give you an example that you can maybe understand easier. Retractable landing gear. You probably noticed that slow airplanes do not have retractable landing gear, but fast airplanes do. It's a classic example of when morphing makes sense. When you're moving really slow, it is not worth the extra weight and mechanical complexity to have retractable landing gear. Retractable landing gear are very heavy, very complex. They add a lot to the airplane. It only makes sense once you're flying past about 110, 120 knots. This chart basically says the same thing. At some point, you're going to have a penalty for morphing. But past a certain speed or capability, having a morphing airplane actually gives you a huge benefit, like for the F-14. So when we are looking at these morphing technology, we didn't just try to make every airplane morph. We really tried to understand, where does it actually pay off? So what this says is for limited speed range, a very small payload, limited load range, you don't really need morphing. When you're trying to do big things, many different missions, fly high and slow and fast and long, that's when morphing really pays off. And this is where we were trying to do our research out here. So, morphing in the 21st century. I'm often asked, what are some examples of morphing today? A planetary explorer. I'm going to show you some videos at the end of how you would morph for a planetary explorer. Also, a high-altitude, long-endurance, remotely piloted aircraft. It's a mouthful. The idea is you would have a flying satellite, an airplane with really long wings that would fly for not hours, but days, literally. And it would be like a cell phone tower that would just fly around. Instead of an ugly cell phone tower, these would fly around days, even weeks or months, for example. So what's the problem? So, do you have an airport that's got wings that stretch many, many feet? Probably not. And airplanes with wings that long and skinny that you would want for like a cell phone tower, they can't take off. The air is so heavy at sea level, we've tried, by the way, and the wings are too long and skinny, they're floppy. So the wings you need at high altitude are not the same wings you need at low altitude. Another example of why you would morph. There are many other examples here that I can give you examples on. In the military, they're even more obvious. You want to combine supersonic with an attack. Basically, you want to be able to jet out there to the battlefield and then attack the person while you're there. The airplane you would want to go really fast is probably like the Blackbird, a really high-speed Mach 3 airplane. But that airplane that moves really fast, it can't attack you. It's too big. You need a more streamlined airplane to do dogfights. So an airplane that can go really fast and then become really tight and all of a sudden do a dogfight would be great. So a lot of military examples as well. What we're trying to do is the same thing that we did in history, but now we're actually, of course, dreaming and asking for even more out of the airplane. So now on to some of our examples. These are examples from our laboratories, things that we've tried and done. One of the things that we've learned in doing this is that one size does not fit all. What worked for one concept will not work for all of them. So here's one thought. We looked at many different design requirements. We said, are we going to look at work coefficient? Is that the main thing we need to worry about for morphing airplanes? What about deflection? It's all about how much the wing deflects. So then somebody else would come in the room and say, no, that's really crazy. You know, our physicist said it's all about power. You know, that's all you need to worry about. The structures guy said, forget that. It's about weight and stress factor. The aerodynamicist said it's frequency ratio. That's all that really matters. So we literally would have fights over what really mattered to make a morphing airplane. And there's no final answer, by the way. The answer really is it depends on what you're trying to do, is what it really ends up being. This is one concept we tried. It's called the fishbone. It was really modeled off of a classic fishbone. All of these little bones on the end move. Looks really cool, so what's wrong with it? You know, we built simulation models of it. Even though this works really great, once you put skin on it, it required so much power to move all the bones that it really didn't end up being a very good concept. You would need a skin basically made out of rubber or tissue paper for this to work really well. So this concept was a really good idea, but maybe not good in the end. Another concept, our space guys, you can notice in space there's a lot of what we call truss structures that kind of look like this over here. Our space guys said, well, you know what? Space, these little truss structures work really well in space. Let's try them on the ground. So we built a wing based on a truss structure. And there's a structure here and here, built very similar to you would do a space station. But we had to connect these things. So we have clamps, we had actuators, and then we needed a skin to put over the in-between parts. So each one of these pieces was a research project all by itself. We had somebody just figuring out how to put the skins on it. We had someone just working on these clamps, because once this thing starts moving, you have to stop the wing from moving at some point. So we needed a break, literally, in the wing we had to create. So every part became so complex. And then the analysis of it, a kinematics analysis of all the moving components inside. So this wing actually worked really well. We probably need to actually fly it to give the final test of it. Another example of a wing concept. In this case, what we tried instead was just focusing on the trailing edge. So think of feathers, right? What we have on airplanes today are a big, large flap that deploys. Instead, birds have a bunch of different feathers on the trailing edge, right? So how would you make that work? Well, He built feathers. Here's one little feather all by its little lonesome self. And we tested the little feather all by itself, going backwards and forwards. So this guy was the joke for a while. He's in his lab with this little thing this big going like this for weeks, trying to get it to work. And we were just laughing at him, saying, "This is your research project?" And then he says, "Well, I'm building a wing." We're like, "Yeah, whatever." Anyway, a few months later, he actually took many of these things and put them together on the back of this wing, basically to like little feathers. His idea was pretty simple. You want to be able to control the fluid motion over every single part of the airplane, from the root of the wing all the way out to the tip. And let's do that by having many different little control surfaces. He took his wing and put it in a wind tunnel at a university with students and tested it out. And he showed, hey, I really can control the lift all the way across the wing wherever I want it. He also did simulations where he made many different shapes of this concept. Then he actually put it in a large wind tunnel. We had an old model of an airplane. He took the old model, dusted it off, and put his concept on the back end and put it in a wind tunnel. And he actually showed that he could control how the entire airplane moved. And you'll see it in just a minute. He was actually able to roll the entire airplane and control it using these simple there it is. The only thing controlling that airplane are all those little teeny feathers, believe it or not. And this airplane was perfectly controlled. It was not out of control at all. He had it completely in control. So basically, this is similar to bird feathers. He would say, this is coefficient of pressure, which is the air pressure on the wings. He would say, I want the pressure to be here, and push a button, and it would send a signal in, and the little feathers would go in the right place to make that. Then he would change it and say, nope, I want it here right now. Then the system would change and catch up to him. Then he would say, nope, go back to here. And it would follow him. And the wing basically moved anywhere he wanted to, beautifully, just like a bird would. So, from a silly little idea in a laboratory, to building a simple wing, to getting a whole airplane model in a wind tunnel, he actually showed this worked marvelously. So, in the end, how did we actually evaluate all these concepts? Which one actually works? Weight is often a common thing. There's often a joke between aeronautic engineers and civil engineers. We say for a civil engineer, when they need to fix something, they just add more cement. For an aeronautics engineer, you have to make the thing lightweight. So you have to be smarter than that. We can't just slap on cement. So your trick as an aeronautics engineer is to make the thing as light as possible, but as strong as possible. So weight is everything. Every pound of weight is millions of pounds of fuel. So what we did is we basically looked at a bunch of different airplanes that have flown before, and we compared how much load they could carry with how much they weighed. And historically, they line up like this. So in a very simple way, we could say that historically speaking, if you're above this line, you're okay. You're kind of weight efficient. If you're below this line, you're not very weight efficient. So basically, it's a comparison of how much your wing will carry and how much it should weigh. And it gave us some idea of evaluating different morphing concepts. So now, more ideas. Exploiting aeroelastic effects. I spent a lot of my career doing aeroelasticity, the study of airplane flexibility. No, you don't want the wings to be flexible most of the time. Most airplane wings are designed to be as stiff as possible without adding too much weight. Well, let's think of it differently. Are bird wings stiff? Do bird wings bend and twist? Of course they do. And birds actually exploit their flexibility. So our idea was pretty simple. Instead of fighting the flexibility, use it. Instead of adding more things in the wing to make it stronger and stiffer, let the wings flex and use it like a bird would. So I'll show you two examples of how we did this. By the way, people thought we were nuts when we first suggested this. Absolutely nuts. And my answer usually is, thank you. So, one concept. This idea came from a student at the University of Florida. He was a windsurfer. And he noticed on a windsurf sail how the windsurfer kept control over the windsurf. When a large gust of air would come, two options. One is the gust of air would throw him over into the water. The other option was that the sail would basically move out of the way and get rid of some lift so that the windsurfer would stay up. And so if he had a rigid sail, it would just plow him right over. But a flexible sail, just move out of the way, get rid of some of the air, and you can go and then snap back to where it needed to be, right? So what about an airplane wing? What if you made the airplane wing so that when a gust of air came, instead of making the whole airplane jump, the airplane would just get out of the way, let the air go away, relieve some lift, what we call it, and then go back to normal again. A little nuts, right? Well, for a small airplane, it makes a lot of sense. The smaller and smaller we made airplanes, like micro and nano airplanes. This airplane was, I think, only 6 to 8 centimeters wide, this little yellow one here. These little guys, when the gust of wind comes, they're all over the place. They really can't fly. So we tried this idea. This is as flexible as it looks. This is someone's hand. This material is really like a latex glove. We started by taking a glove you would use, like for a doctor, just cutting some of that same material and placing it on the wing, very flexible. The only thing even mildly rigid were these little pieces in the wing like this. And even these were pretty flexible. So we took this thing, and as usual, NASA, we built a model. We built this model, and we put a little engine on it with a little teeny propeller that was about this big, and we put it in a wind tunnel. So here are 2 videos of what the wind tunnel test looked like. First, look at how flexible these wings are. This is what it looked like in there, and we're watching this saying, this is nuts. You know, everything you learn in aeronautics says wings shouldn't do this. This is not what should happen at all. But it did, and we, you know, being good engineers, we just took the data and see if we could understand what's happening. So, let me go to the other video. On this one, you can really see, this is smoke. We use smoke in the wind tunnel to give us better flow. This is a side view of the same airplane. You can see how the skin is bubbling up. The engines are actually on. The air is flowing in the wind tunnel. This is all the data we're taking coming out of the back of the little airplane. So then we take it up and put it in the smoke. And you can see what's neat about this, the flow stays with it. It's not coming off. Look at how much the skin bubbles up on the little airplane. This is nuts. Airplane wings, again, aren't designed to do this at all. But the little wing stayed there, and it actually worked very well. Again, tiny little airplane, 55 grams empty weight. Tiny, tiny thing. Cruising speed, top speed, 35 miles an hour. Whew, tell you. Okay, so some data, some real data. This is one of these I told you so. Our aerodynamicists, our fluid mechanics folks said this will never work. You're never going to get the same data twice. One day you'll get this information, the other day you'll get something else. It will never work. Well, it turns out this is lift over drag, a common character that we looked at over angle of attack. Angle of attack is how much the airplane is nose up or nose down. The thing stayed on every single time. The data was very, very repeatable. Very repeatable. Really great data. We compared it to this black stuff here. The black line is the rigid. We made a completely rigid wing, and this is the black one here. And these are all the ones that are flexible. They're all basically the same. The theory was that things that's flexible, you won't get enough lift, but it gave exactly the same amount of lift as a rigid wing. So why would you go with the more flexible wings then? Here was the thing that really paid off. This is coefficient of lift. Basically, just think about this as lift. It's non-dimensionalized lift of the airplane. This is angle of attack. On an airplane, while you're flying, what you have is a stall speed, a stall angle of attack. At some point, and you guys do this when you're in the pool or with your hand outside the car, at some point when the airplane noses up, the air is going to separate behind the wing, and the airplane can no longer fly. That happens on this curve when it falls off like this. This curve means you've lost all the air flowing over the wing, and it's going to stall, and you can't fly any longer. The rigid wing stalled at about, 15, 16 degrees. The most flexible one, that was latex, rubber, only 2 stiffeners in it, went all the way out to 35 degrees angle of attack. So one wing, 15 degrees, it lost it. The other wing, 35 degrees, nose up. Perfectly good, no problem at all. So people ask, how can a fighter airplane fly like this? You have to have that kind of control. And in this case, what we found is a flexible wing can actually give you more control than a rigid wing. It defined all the theories for most people that we knew. So, one more example. This is called the Active Aeroelastic Wing Program. Truly a novel idea. I mentioned that most airplane wings are made rigid. The idea here instead is make the airplane flexible. Now do it on a fighter airplane. No more tiny airplanes. Let's do it on a real big airplane, right? Well, we shall see. On these bigger airplanes, the problem that you have at really high speeds on the airplane, if you use the aileron, one of the flaps on the back end of the wing will twist and break, believe it or not. So fighter airplanes, when they're at really high speed, they cannot use their control surfaces on the wings any longer because they're so fast that when they move an aileron, it'll literally twist the wings too much and break it off. So they have to use their tails for control when they're actually in a dogfight, believe it or not. So instead we said, let the wings twist and just control it. It defies our normal logic. So we did wind tunnel tests. We built many, many models. We did a lot of computational fluid dynamics research over many, many years. 15 years later, we finally got to flight, believe it or not. We actually took an F-18 and put it in the air with a pilot aboard. We took an F-18 and we remade the wings. We took out pieces of the wing to make it more flexible, literally. These pictures, you can see the guys from the companies going, this will never work. We're literally ripping out pieces. Don't need this, don't need this. We're going to make this F-18 wing more flexible in the end, but we're going to use advanced computers to control it while it's flexing, and you can actually get more control. The reason why this is revolutionary is because for fighter airplanes, for all airplanes, you do not want weight in the tail of the airplane at all. If you think of a dart, the weight's in the nose, right? The dart will not fly backwards. You have to have weight in the front of the dart for it to fly. So when we had to add weight to the tail of the fighter airplane to control it, not a good thing. We had to do it. So if you can get rid of that weight and start using your wings again for flying, you can make the airplane much more controllable and better in flight, in war, for example. So enough talking. Let's look at the video. This is a video of the F-18 in flight. It was a modified F-18 taking off from NASA Dryden. And this video is kind of slow, but the good news is you can see it because when it's high speed, it's really almost impossible to see the wings. The wings look normal from the outside. They really do. What you're going to see is he's going to go into a turn. This is a turn where he's just using the wings, and the wings are actually flexing in a really small fashion. This is a close-up of the wings. Look really close, and he's going to go into a turn. You can see the wings actually twisting. Normally, you'd never let that happen, but it's just a demonstration of you can roll the airplane, let the wings twist, and control it even while it's twisting. So, those are all examples of changing shape while you're morphing. What if nothing changes shape? Are you still morphing? Flow control. Many of you are taking fluid mechanics. It was our fluid mechanics expert on the morphing team that said, I want you to try something different. I want you to think about using micro flow control. You know, I'm a structures person. I like to build things. I'm like, flow control? How is flow control going to help morphing an airplane? Little teeny puffers. Come on. We want big beefy things to move. You're going to twist a wing and bend it. And he said, no, come on. You can do really cool things. Another reason why you need teams of engineers. So Tony Washburn is his name. And Tony said, let's try flow control. So enter flow control. Here's an example of a wing. Notice the wing itself is not moving at all. Look at the flow. We changed it from that to that. And we didn't move anything on the wing. So this is the magic that the Wright brothers talked about. What the heck are we doing here? I'll play that again for you so you can see it. In flow control, you have little teeny puffers, believe it or not, that suck and blow really rapidly. They suck the flow in, they spit it back out. If you put them at the right direction, you can move the flow any way you want. It's completely a fluid mechanics problem. Completely fluid mechanics, without question. So your professors are not going to give you a fluid mechanics problem to solve. So you don't need to move anything, and you can move the air. So you can morph without moving anything. Pretty cool. How on earth do you do this? Let me show you. I mentioned smart materials were the foundation of all of this. So the idea of microflow control, a lot of big words here, but basically you're taking advantage of unsteady aerodynamics to reduce the energy requirements of the airplane. You actually are going to use flow instabilities instead of, normally we want the flow smooth. In this class, we're doing the reverse. We're making the flow unsteady on purpose and controlling it. And you can use that to your benefit. Again, bird feathers do this all the time. So how it works, basically, is first you have to create the little sucking and blowing thing, right? So here's how it works. This is the surface of the wing right here. You make a little slot in the middle of it, and then you have a little diaphragm that goes up and down. So you suck the air in and spit it back out really, really fast. So first we had to make these little devices. So we use these piezoelectrics that I mentioned to you earlier. Things that pump up and down like that. Here you go. This is a piezoelectric actuator. This is a built-up version of this. So this is the idea. We built it up, little teeny slot on top. Notice, because it's a smart material, there's no gears, there's nothing, no mechanical part, just a couple little wires to make the little heartbeat. One of the benefits of smart materials. We take this, we put it inside a wing. This is the wing. There's a little slot right here. Normally at the very beginning of the wing is where the flow gets ugly. So that's the idea of this. So will it actually work? This is our simulation of what the flow looks like coming out of the jet. And this is what happens when you turn the air on. This is going to look really strange. But this is a simulation of the actual jet. It's pumping in and out really fast, sucking in and out. So a lot of people ask me, so you're going to have these little holes on an airplane. Will this actually work? Won't it clog up in flight? Well, if you suck the bug in, you're going to spit him back out. In a little bit different format, so normally they do not clog because what gets sucked in gets spit back out. So did it actually work? This was actually in the late 90s. This is a wing in a wind tunnel. This is smoke that we're using on the wing. Again, the wing is kind of sitting up really high. Normally the wing would stall because flow is really separated behind the wing like this. We have jets on this wing here at the front and near the back, right up here and right back here. With the jets turned off, the flow is unstable, unsteady, and the wing has stalled. You put the jets on, it's beautiful. Nothing's moving, and we control the airflow. It actually worked amazingly. We took this data. This is, again, lift, coefficient of lift, non-dimensionalized lift. Without control, this is how much lift you got. With control, you got a lot more lift. The development was rather amazing, and it has revolutionized how many aerospace companies are designing their wings of the future, believe it or not. Today's wings look kind of like this with large flaps coming off of them. Tomorrow's wings, if they use this technology, can start looking like this, a smooth one-piece wing. And you can only get that if you can control the flow using these small little microjets. So this has led to many, many large changes. So again, we built a lot of models. This is all research and development. We built several different models. Here's an example of a wing. We built this airplane model. We put it in a wind tunnel, right? The idea was to put a lot of different jets on the front of it. What we wanted to do was to control the entire airplane just with jets. Nothing moving. Is it possible? Don't move any flaps or ailerons, no rudder, no elevator, nothing. Just use little teeny jets, little puffer jets that I teased my colleague about. We wanted to just use those. And this was his program, by the way. There's Tony right there. There's his name. Tony and Irene worked on this. Tony is a fluid mechanics expert. Irene is a flight controls expert. So we had a controls person working with a fluid mechanics person to make this actually work. Tony understood how the flow needed to be. Irene understood how to control the airplane. So the two together made this project actually work really well. So Tony and Irene built the model. with Irene's help, they decided to put the jets in these locations. They took the jets and put them in. You can see them all in this is what the actual wing looks like on the inside. And then we flew this in the wind tunnel. And to our amazement, this is data from the wind tunnel. You can go up and down. You basically could do anything you want. You could get as much lift as you wanted. You got lift, really, really good lift. And then also, if you wanted bad lift, you also could. Why would you want bad lift? Why would you want to reduce your lift? To turn the airplane. When you turn an airplane, you reduce lift on one side and increase it on the other side. Normally, you deploy ailerons to make the airplane turn. Instead, you don't move anything. You just turn jets on one side, reduce the lift on the other side, and the airplane turns with nothing moving. So more pictures of my hands out. I don't know how you're going to explain this. I really am crazy. Anyway, so when people have said, are you guys really envisioning future airplanes would actually be completely smooth with nothing moving on it? Yes, because we tried it and it actually works. We were able to roll the airplane and control it, and it worked actually quite nicely. I'm going to show you a video of this, and what you're going to see in the next video is the flap, the back flap of this. Because there's nothing moving, we had a hard time showing people how this actually worked, so we did something that was a little backwards. We turned the air on, and we intentionally made it really unsteady, so the wing was bouncing around a lot, and then we turned the jets on to show how it became really stiff. It was kind of a backwards way of showing it. But that's what you're going to see in the next video. So, we call it the stingray. So this was, you can see it bouncing around a whole lot. This is with the airflow off, without the jets on. You turn the jets on, and it becomes smooth. This is jets on. You can see the little things become, and then you turn it off, and it becomes flexible again, bouncing up and down. So again, we did it sort of backwards, where we were trying to show lots of motion. There it is, lots of motion, lots of beating around. And then you turn the jets on, and it comes still again. So we were able to control it quite nicely. So some lessons learned from all this crazy morphing stuff. Know when to morph. It doesn't always pay off. Don't torture your airplane. Do good things to it. The second thing is understand the mission and the system's level requirements. We would often solve one problem. The guy with the feathers, or those little things that went back and forth, he got a million phone calls. I want your technology on my airplane. Put this on this airplane. Well, it won't work on your airplane. It only works on some airplanes. So understanding what you need to do is really important. And then, and the shape change is not the goal. We weren't trying to change the shape of the airplane. We were trying to make the airplane more adaptable. And as our fluid mechanics colleague told us, you can do it without even changing the shape. Designing and modeling the morphing concept, wow. Many have asked us, can you really model all these things? Do your computers analyze all of these things? No. Many of the things we did without the benefit of some great mathematical tool, because they are not yet invented. Most mathematical tools are designed on very known systems. This is not known. No one has done most of the things I showed you. It was the first time they've ever been tried. There were no computational tools. We made the best use of what we had. Used a lot of engineering judgment, and we built things. We built things, tested them, broke things, and learned from them the old-fashioned way. And it is still the way of making engineering discoveries, is to build and test and try. And then when we do that, we do develop tools afterward that can model it. It has to fly. This is from our aerodynamics colleague. Says, you guys think, you structures people think you can build anything. And his comment was, don't forget about aerodynamics. The thing's got to fly. And sometimes a little teeny puffer jet, those little jets are the size of your fists, little teeny things. And it was unbelievable to us all that a handful of little teeny jets the size of your fists can make an entire airplane turn and change shape in the sky. But it actually worked. So how do you cover it? The skins, wow. When we naively thought, okay, we're going to make this super duper, totally flexible skin. You're just going to stretch it over the whole wing, and that'll take care of the whole problem. Totally dumb. So it did not work. What ended up working, again, think back to biology. On your body, some of your skin's really, really rough. Some of it's really flexible. If you had the skin that your palm is made of on your eyelid, you would not be able to blink, okay? It would be too stiff. It's a silly example, but you know what I'm saying, right? On the airplane, it's not any different. Some places on the airplane wing, we need a really stiff skin. In some places, we need a really flexible skin. The challenge, so we can do that, right? The challenge is connecting the really flexible skin with the really stiff skin. You just can't sew it together. And so this is still a huge challenge, is how do you cover it? And designing different types of skins for the airplane that will all come together. We've tried many, broken, there are pieces of skin, airplane skin concepts all over the place at NASA Langley. But our big lesson learned is we really need to blend all the different types that we have. And then last is the control. I mentioned my colleague Irene Gregory. How do you control it? Even when we would come up with these ideas of bending and twisting wings, you know, our controls folks would say, how are you going to fly that? When do you bend it? How much do you bend it? And how are you going to keep the airplane stable? Our controls people, many of them are actually electrical engineers, believe it or not, because control theory is based a lot on electronics. And these are the ones that keep our airplane stable and in flight. So this project required a lot of different types. We had chemists, physicists, double E's, electrical engineers, aerodynamicists, fluid mechanics, structures, materials, all types of different people that were coming together to make it work. And their lesson to us was that what we really needed was to do what birds do. Just instead of having one large flap, have many different ones. So you can control the airplane any way you wanted to. So now, I'll finish with morphing with the aliens, flight in other atmospheres. We were thinking about, at NASA, what about having an airplane that would fly on Mars or on Venus? Wouldn't that be cool? All of you, I'm sure, have seen the Mars rover, the little thing that rolls around on Mars is really kind of cool. Well, you know, we're airplane people. No stinking rover. We want to fly, right? So how do you get an airplane to fly? Our colleagues at the Jet Propulsion Laboratory told us we were nuts, as usual. And we said again, thank you. So, how do you get an airplane to outer space, and how do you develop a morphing airplane for space flight? First small problem is getting there, right? So you launch your capsule. You have the bottom of your capsule comes off, parachute comes in. You have to unfurl your wings. The wings pop out. It's a good thing. And then you release the airplane, and it comes out, and you start spinning. The idea is you would have, you know, solar cells potentially to give you the energy that you need to fly. So this is just to get there. A very complicated thing. It's a very long flight. Next, you have to test it. The next video you're going to see takes, this video was a cartoon. This was the dream. This was the idea. Several engineers at NASA Langley came up with a folding wing Mars airplane. But they had to test it. How on earth do you test it? You get a large balloon, really, a very large balloon. We took a high altitude. Our cloud, this is where you get different disciplines. I mentioned very early, if you were still awake, that we also do cloud research at NASA Langley. For our cloud research, we launch very large balloons that go very, very, very high up and take cloud data. We took those same balloons, but this time we put an airplane on the end of it. And we released the airplane 100,000 feet in the sky. To give you some perspective, when you're flying in like a 747 or any large jet, you're typically at around 35, maybe 36,000 feet. So we released this airplane at 100,000 feet, 3 times higher than you normally would. What you're going to see in the next video is the airplane gets launched from the balloon. It's way up in the sky. As it comes out, just like what you saw, the wings unfurl, tail comes out. At first, it's in free fall. It's just spiraling down to the earth, completely out of control. And our control system, again, our electrical engineers take over. And the electronics are fighting like mad. They're just going to town trying to control this little airplane. You'll see the wings going all over the place. And finally, it gets control, and it stops, and it gains control, and you can see the Earth's horizon. So I'll play the next video. So this is the parachute. You're looking back up into the parachute. It releases, and it falls. That's the Earth below. Next, you're going to see it's wild. Now it's just flying. The wings are going to pop out in just a minute. It's still in free fall. There the wings pop out. Look at the control surface. It's in complete free fall, totally out of control. It's trying, it's trying, it's trying. Again, there it is. It's got control. And then it pulls up. It's going nose up, slowly, slowly, nose up, nose up. There's the Earth. At that altitude, you can actually see the curvature of the Earth. And now it's flying. It's probably, I'm going to say, at 70,000 feet by now. Way above. And this bird, now look at the control surface. It's pretty smooth right now. It's an absolute controlled flight. And it comes in for a beautiful landing on Earth. So, the next video is how do you actually fold it? So first you take the baby and you turn him over. Here we go. Turn him over. Take the baby's arms and fold them in, one at a time. Then you have the baby's tail, tuck him in. Put him in his basket. There you go. Then cover him up. And he's ready to go to bed. There you go. So there's the Mars airplane all packaged nice and neat. To give you a true story that may be kind of sad, but to tell you how science worked, our engineers at Langley designed this exact airplane and did these tests that you saw. They were trying to fly for the Mars flight in 2009. They did an amazing amount of testing to analyze this concept. And in the end, they were not chosen. They just learned about a month ago that they were not chosen for the 2009 flight. So they must wait till 2011 for the next flight. So it was really heartbreaking after all this research that they were not chosen. But they're going to continue on to look out for it in 2011 to fly then. So, in summary, morphing airplanes began in 2003, actually in 1889 with Otto Lilienthal, but they've continued to evolve and they will continue to evolve. As long as we keep asking more from the airplane, we're going to keep wanting to do more morphing with the airplane. But the most important thing is to morphing for the mission, beginning with the vehicle requirements. What are you trying to do? And then actually going to the actuators and materials that you need to make it happen. Knowing when to morph. It doesn't always pay off, as I showed you earlier. You don't always need little puffing jets. You don't always need twisting wings. For some of our most simple missions, the old-fashioned airplane concepts will work just great. I say this because I get a million phone calls from people, make my airplane wing morph. Sometimes like, you don't need me, honey. Just take an average airplane. It'll work just fine. Knowing how to morph. Well, we didn't know how to do this, I'll be honest with you. You saw many concepts that we tried. Some of them worked well, some of them didn't. We had to, I mentioned integrated capabilities. We still need to be able to integrate the flow and the structures and the controls together in one nice tool, one nice simulation tool. So we can do what I talked about earlier, sit in a simulator and fly your morphing aircraft. We're not there yet. We're still building wings and pieces of wings and tails. It'll take us some time to get to the complete airplane. The dream airplane, I should say. We've done pieces and parts. It has to fly. Adaptive aerodynamics, fluid mechanics may be the morphing technology that saves the day. Nothing's changing shape, but those of you that are in physics that might be looking at fluids as an area of research, you might be the ones that end up making the morphing airplane a reality, more so than us wackos that want to bend the wing. Materials are still a critical issue. Our chemists at NASA Langley are still the heart of our effort. They are the ones that can create these crazy materials. Even our fluid mechanics people, to make their little jets, it began with a new material idea. And our chemists are the ones that basically created those. We've made passive materials for flexible skins and these new bionic active materials for better actuation. Every year we create some new active material that can morph and change shape. And every year we try to dream about how can we use that to improve the airplane. So, nature. We've learned a lot, but sometimes we're not sure exactly what to look for. In our studies of biology, what we've learned is that sometimes things are counterintuitive. We think that in airplanes it has to be smooth for it to fly better. Nature taught us that roughness has its place. It can actually make the airplane better. Nature also taught us that big isn't always better. One really fun example is that the lizard, the gecko, it can climb the wall of a fish tank, a glass fish tank, even when it's wet. We had no idea, how can it do that? Well, there's clearly suckers on its feet, but even when it's wet, how can it do that? If you look at its claw or its paw close up, it's fascinating. As engineers, what we would have done is put 4 big suckers, one on every foot, right? It's 4-wheel drive. Make them bigger and badder, and it'll stick, right? Nature didn't do that at all, because our idea would not have worked. Instead, on his little foot, there are millions of tiny suckers with a little bit of glue on every little sucker. Tiny, tiny ones that the naked eye you can't even see. So it is not 4-wheel drive, it's a million-wheel drive. Every paw has millions of little suckers and little bits of glue that come out. So basically, at any point, 1 foot can stick on the slipperiest surface, because even if some of those little teeny suckers are not working, other parts of his paw are. So the idea of bigger and badder doesn't always work. Smaller may actually save the day, and the idea of flow control showed us too. The smaller little puffer jets may actually, in the end, work as well, if not better, than big, huge flaps that we use today. Again, that lesson came from nature, not a common thought that we would have had on our own. So concluding remarks. Technical challenge. One of the hardest things we've had is working with totally unconventional technologies and knowing how to use them. Even when we had a really good idea, we often didn't know exactly how you would put them on. If you study history and you look at how technology was advanced, some of the best technologies came from a mistake. The guy that came up with the mask, the little mask you use for painting, that was a failed bra cup, okay? His colleagues put the failed bra cup on their face and were walking around the 3M laboratory to joke him about how terrible his bra cup was. And they ended up having better breathing and less problems. And so that's how they ended up discovering the infamous mask that you wear. So when you put those things on, you're wearing a bra cup, by the way. So I say that here because many of the things we work with, they're unconventional. We didn't know how to apply them. We just had to build it and try it. Sometimes try them in really unusual ways. And sometimes it works and sometimes it doesn't. One thing that we have learned, historically, retrofits dramatically underuse the technology. What I mean by that, a retrofit means you take the same thing, just glue something new on it, and you really can't get the best benefit doing that way. The most obvious example is in a car. You can either use a carburetor or a fuel injector. You can't retrofit a car with a carburetor with a fuel injector. You have to rip out the carburetor and pull in the fuel injector to really use it. Many of these technologies are the same way. To use them really well, you've got to get rid of the old stuff and really start from scratch and redesign your system to do it just right. Not an easy task. Risk and learning are part of the fun and success. Test early and test often. Get used to failing. Every student in here has had a failed project. It's okay. Most of your professors, if you know what you're doing, will give you some credit for trying. If not a lot of credit for trying. We even fail at NASA sometimes, but that is how we learn. It is also how we discover, honestly. Our performance demands, we do want more and more from the airplane, and we're going to continue asking them to do a lot more as the future goes on. And so many folks have asked me, are we done with morphing? My guess is not. As long as we keep dreaming, keep pushing the envelope, we'll continue. Right now, I'm working on a project with the Defense Advanced Research Project Agency, where we are building morphing wings. We've already tested them in a wind tunnel. One wing folds up like this. The other wing changes shape, it stretches back in flight. We are actually building small model airplanes of this exact concept and plan on flying them in just a few months. So be looking out for these flight tests. So we're going to keep trying. From folding wings to stretching wings, the future is still ours to behold. And the results keep coming back and fascinating all of us. So with that, just going to say thank you and take any questions.
Hi.
Hi.
My name is James. I would like to know, what are the limits of your R&D division? I mean, like fund limits or government limits, I don't know.
What are the limits of the research?
Yeah, the R&D division.
Oh, for the overall aeronautics or for morphing?
For, well, I don't know, whichever.
Well, mostly we're limited by money, frankly. What limits us is the time and the resources. We often have a huge, when we get together to think of what we'd like to do, the many things we like to do we have a long list. I've only shown you a portion. We are usually limited by capability and creativity, believe it or not. One of the reasons that I was asked to do this is because I was a young engineer at NASA and I didn't know any better. Very often you can limit yourself by your own creativity. You think, well, we've tried that before, it won't work, let's not try it. So creativity has been one of our limitations, and funding, frankly. To do these tests, it is not cheap. The Morphing program that I manage, it was $35 million per year. And I managed it for 5 years. It's a lot of money. We had, again, over 30 universities involved, 100 researchers at NASA Langley coming together. And so a lot of testing, a lot of analysis. It is very expensive and time consuming. So time and money and creativity are perhaps our biggest challenges. And not losing heart, frankly, along the way, because a lot of our ideas didn't work at first. And a lot of people just flat out told us we were nuts in the process, and that kind of gets discouraging. But my boss has been always very supportive, and NASA researchers have been very supportive. And in fact, I think I told some of you this comment, when I first began this project, and I would talk about this to other people, I got lots of strange faces like, you're doing what with what? In our biologically inspired work, I didn't even describe many of that, but we were looking at fish heads and hummingbird wings and bones and scales and skins and all sorts of strange things, and even muscle tissue. My boss actually told me, Anna, don't get disheartened. The first time that you talk about morphing and people do not think you're crazy, I'm going to fire you. It should make people think you're crazy. It should be beyond what most people dream, because that is what NASA does, is push the envelope. And so we intentionally try to make ourselves go beyond what is considered normal. Anyway, I'm not sure if that answered your question or not. Other questions?
Hi, I'm Daniel.
Hi.
I was wondering, have you thought of applying this technology to other things, such as robots and stuff?
Oh, yes. What a great question. Yes. Smart materials, these materials that I described earlier, are being used in a lot of different things. In fact, wow, there's a lot of different really cool areas. The toy industry is using a lot of them, for example. But robots are using smart materials to move the arms, where the fingers are all, instead of having, again, to make a finger move, you could have a bunch of little gears in there, or you could have these smart materials that will turn with just electricity, for example. So yes, many of the concepts that I've shown you here have been used on many things that fly, helicopters, little teeny airplanes, very large airplanes. They've been used on robots, many different areas. Shower heads even, the anti-scald shower heads, many of them are made with shape memory alloys, the things that change shape when heated. It gets too hot and the thing automatically shuts without having to have a temperature sensor on it. So yes, there are a lot of really cool examples of using these materials in all sorts of really realistic looking concepts. Some of the toy companies and the animators that we've worked with, in fact, have taken, some of the materials we have are like Rubber, the electroactive polymers, are really flexible, and they look like a beating heart when they're moving. And so they will take them and make them the eyeballs of a thing. And so it looks like the eyeballs are moving around. It's really spooky. And they color it the same way. So yeah, some of the creative ideas that they come up with to us are just amazing. I was telling some folks at lunchtime, we ended up working with some medical doctors that are making prostheses joints in muscle tissue. And we actually use some of our work in microelectronics and fiber tissues to help them with making prosthetic muscle tissue, believe it or not. So yeah, the number of different applications is rather amazing. I am surprised when I get a phone call and say, hey, do you know what we just tried? And it never ceases to amaze me. So yeah, the opportunities are really, really broad. There's a conference in the US every year, it's coming up in about a month, that a lot of people gather that talk about how they've used these materials. And every year I'm amazed and blown away at the things that are made to squish and morph and bend for many different ideas. Some of them are pranks, of course, on parents and brothers and sisters, but anyway, it's okay.
Hi. All this cutting-edge technology about morphing aircrafts and smart materials, it sounds really cool, but don't you think it might be a little expensive to actually implementing it into aircrafts and flying commercial airplanes?
Yes.
I mean,
I'm being a little silly. No, you are correct. New technologies typically, it's actually a very, very good question. I mentioned earlier that using an unconventional technology requires some risk. We had done some studies on just looking at how technology advances, and I didn't bring some of these, but it's actually a very good question. Every new technology at the beginning is too expensive and too costly. The laptop is a really interesting example if you've ever studied the development of a laptop. You know, people said, why would anybody want a small, slow computer that's portable? It has less memory, less physics, all those sorts of things. And they were extremely expensive at first. And then, of course, the technology was refined, and most of us end up having laptops to do what we want. So you are exactly right. In the early phases of every new technology, it is always going to typically, it may outperform the newer technology, but it's going to be much harder to use. It's not any different. I mean, I'm going to give a silly example, by the way. When cars were first invented, if you remember your history books, right? Those on horses would laugh at those in cars and say, you know, get a horse, for crying out loud. The horse never breaks down. You know, we always have a horse available. Cars were more expensive, they were more complex, and they broke down in the early stages of automotive technology. And those on horses really laughed at those that had the cars. But eventually, as we developed the car, of course, they took over. So you are exactly right. And in fact, your question's a good one, that for some of our newer engineers that come to NASA, it is easy to lose heart in the early stages of a technology because you want your technology to be used tomorrow morning. It is so cool. How can they not want to use my idea on the next airplane? Because you have these great lab results, you know? But it does take often decades or a decade or more for a new technology to get used because at first it is more expensive and we don't understand it completely. And so we tell our newer engineers and researchers to take heart. Some of the best inventions took 10 or 20 years to come to fruition, but many of those end up revolutionizing the world. The laptop, the car, the airplane. There's many really interesting examples. We actually spent some time studying a little bit of technology development history to give our researchers that were working on morphing technology some heart to stick through it. That eventually, maybe you may retire before it is used, but you can look at your grandkids and say, I did that. It was my idea that paid off. So it's a very good question.
Hi. For the aerodynamics control that you present in your presentation, sorry. Se me fue lo. ¿Me puede traducir alguien, por favor? Bueno,
Okay. For the aerodynamical control, which Reynolds number is the range that you have to use?
Good question. It depends. Some of our technology works really well at low Reynolds number. Some of it works best at higher Reynolds number. Some of it is Reynolds number independent. So it really depends. Really interesting, those little puffer jets. Reynolds number, for those of you who don't know, is a ratio of the fluid viscosity with the structural viscosity. Water has a very high Reynolds number, or maybe a very low Reynolds number. It's very thick and viscous. High-speed, high-altitude flight has very high Reynolds number, very low viscosity fluid. So often the technologies that, a propeller that is used for a ship is shaped very differently than a propeller on the front of an airplane because the viscosities are different between the water and the air. So your question's a good one. It's correct that typically aerodynamic technology that you would use at one Reynolds number or viscosity is very different than what you would use for another Reynolds number. Really interesting to us, these little puffer jets, these things that suck and blow, it doesn't matter. It's one of the few things we have ever found. It doesn't matter. It is Reynolds number independent. Blew us away, frankly. And people still don't believe us, frankly. We have to show them the actual results. No, really. Yeah, very, very highly unusual characteristic to have something that's Reynolds number independent, but that phenomena is. Most other things are. The idea of roughness, riblets were invented at NASA Langley. And the riblets are little teeny grooves that are put in a wing. And it turns out that riblets can actually reduce drag. It sounds like you want it smooth, right? In low Reynolds number fluids, like water, roughness in the right direction actually is helpful. For high-speed flight, it doesn't work at all. So that's an example where you have to know what Reynolds number you are working with to get it to work properly. So yeah, it's a good question, and we surprised ourselves with that sucking and blowing concept. Very surprising. What's interesting about that, by the way, as a researcher and a scientist, as a fluid mechanics person, so you find out that it's Reynolds number independent. That means that the studies that you perform on your small school wind tunnel apply on a Boeing 747. Pretty cool. So we have had many students do some really fascinating research, and you can say, you know what? This will likely apply in a larger, faster airplane. Yes.
Hi, my name is Sandra Mejia, and my question is, are you also doing research on the fuel or the energy source that these aircraft should have?
Wow. Yes, we are. When we looked at the future of airplanes, several things came to the top of our list. One of them I mentioned is this whole airplane, airspace, and airport concept that we're just going to fly them differently. The other idea is energy. Right now, of course, we use jet fuel and jet engines and things like that. For the future, we will probably not be able to use the same types of fuel, the same types of engines. Interestingly enough, these smart materials largely run off of electricity, or light even. There's some materials that are now working off of light, or heat, for example. So we actually feel like they may help with some of the energy problem. So you can use solar, you can use electricity on the airplane instead of having to use as much fuel. So we have not looked at it discreetly, to be honest with you, but it is one of our top priorities for the future, is to understand how you reduce the amount of energy that an airplane uses in total, electrical or fuel energy. Many other systems, I mentioned earlier on this German company that is now using piezoelectrics to sew their textiles. They found huge energy savings by switching to these little materials, because these piezoelectrics just require a little bit of voltage to move. versus all the gears that required a lot of power to get to move. We are also learning, by the way, I showed you how we're doping a material with carbon nanotubes, basically injecting carbon nanotubes. Now you got me doing an injection thing. That's great. So I'm flying and I'm using drugs. That's what's going to be on the pictures. Good thing my security thing is up to date. Anyway, one of the reasons we were looking at carbon nanotubes and injecting it into a material, carbon nanotubes are extremely conductive. The more carbon nanotubes that we injected into the material, the less electricity that was required to use the material. So even nanotechnology is having huge dividends here. We are finding that we can create these bionic materials that require less and less and less and less energy to operate. And we've really just begun doing that. As we began to understand more and more about carbon nanotubes and other materials like that, and the ability to make designer materials at the nano level gives you lots of capability for the future where potentially you need a lot less energy in general. So no, it's probably one of our top priorities.
Hi, my name is Ingrid, and I was wondering if instead of using birds as models, using flying insects or such as dragonflies or I don't know.
What a great idea. We in fact did just that, a dragonfly, believe it or not. They're ugly things, aren't they? But besides that, the dragonfly's wings are perfectly optimized. You know, being engineers, right, we're arrogant, we can design anything. So we took the dragonfly and basically thought of it as a little airplane. We put in our little optimizer, we put in the weight of the dragonfly and its little mission, a few feet is how far it goes. Even the fuel, it's food, put all that into the optimizer and you hit run. When you do that, out pops from the human done wing, out comes a perfect dragonfly wing. So the dragonfly wing is dead on optimal with the best tools we have today. And so why did we do that? Basically, it convinced us that nature knows what they're talking about. Duh, right? Right. Why didn't we know this before? So with that in mind, yes, people are studying the flight of bugs, literally, and insects for our micro technology. For the military, looking at very small, very mobile, maneuverable airplanes is huge. If you think about urban warfare, if you can launch a little bug that will fly in, fly through a window, and maybe perch on the windowsill, take a few pictures, and come back. You're laughing, but I'm dead serious. It's very powerful. And what's also interesting about the bugs, they're small, right? You launch 5 of them. The enemy catches 3, get 2 more, don't care. The other 2 already had taken the pictures, sent them back to the troops. Shoot those 2 down, we're done. Pictures are already in the computer. Very powerful. And yes, the bugs have it. They're doing it the right way, and we're trying to learn from them. Those suckers are complicated, though, I got to tell you. They really are. And it is true, some have asked, is it true that we don't understand how a bumblebee flies? It is true, that thing should not fly. Really, the wings are too small for the body, but nature does it. So yes, we are learning from a bug. Absolutely, even though they're ugly. Really ugly, I don't like bugs. And those big cockroaches, Because at first our comment was, well, these bugs, even for the little teeny micro and nano airplanes that fly around for the military, they have to carry a little camera or something. The payload on it is actually pretty heavy compared to what it's carrying, right? So do we have any big, fat, ugly bugs that are pretty fat and still fly? Well, those ugly cockroaches fly. So they went from a mildly ugly dragonfly to a very ugly cockroach to look at how these things fly. So yes, very good question. Yes, oh, the tough questions are now going to come. Go easy on me.
There are students here in Monterrey Tech interested in aeronautics. Are there some NASA projects related with master degree programs in some university? And also, in case yes, is it possible for our students to apply for that programs?
Good question. I personally work with a lot of students that are not U.S. citizens, and I don't know, actually I'm not sure what the rules and regulations are, but yes, I mean, I personally work with students that are not U.S. citizens, and so that tells me that some of our programs are open. Some are not, and some are. Many of our students work with us through design studies where we share data with them. We've worked with the university in Israel. In fact, the flow control idea that I showed you, a professor in Israel is the one that Avi Seifert has had many of the great ideas for that. And he still lives and works in Israel and has come to the United States several times. So yes, we can do that through data sharing and things like that. Yes, absolutely. More tough questions.
No, it's an easy one. How long would the Mars airplane be capable of flying, and would it eventually be capable of landing and taking off?
Good question. Right now, they're just envisioning a flight of maybe a few hours to get the data. The landing and takeoff is a pain, as you might imagine, and so they're not focused. They're going to consider it expendable. Once they've gotten their data, they're just going to crash it, is the early idea. Because many of you know, why would you do that? Landing and takeoff are the hardest part of a flight. Flying an airplane, easy. Taking off and landing without crashing, really hard. A lot of people that are afraid of flying or afraid when they get up in the air and they're flying really fast, that's the easy part, that's the safest part. The most unsafe and dangerous part is taking off and landing. And so they complicate everything. So at this point, the easiest solution is to make it relatively expendable. And after it's done with its mission, to have a nice soft crash landing, I say that, without destroying everything. Eventually, the idea is to be able to have a more controlled approach. So, yeah, now the idea is launch from the capsule. And so there's no takeoff, just launches from the capsule, as you saw, and then fly around, and then come in for, I'll call it a rough landing. And we hope it's not too bad. But much of the Mars airplane work is actually available on the internet. I literally think if you guys Google Mars airplane, many of the videos I showed you for the Mars airplane are available on the internet. Just go to Mars airplane on the internet and you can find many of them.
And has a helicopter design been considered for Mars?
Yes, and the airplane actually ended up being better. Mostly because of the unusual Reynolds number and flows on Mars. They're so strange, really. No, good question. That was actually considered very early on, and the airplane ended up being a better idea. Yeah.
Hello, my name is David Tewalde, and I would like to know have you applied any nanotechnology to your skin of your morphing planes?
Yes, we have. In fact, that may be one of the biggest breakthroughs is using nanotechnology. What is really neat about nanotechnology is you have to think about Frankenstein. Did you all see the movie Frankenstein or the Bionic Man? We have made man kind of idea. Well, with nanotechnology, we have a nanotechnology effort at NASA Langley. Our materials researchers, our chemists, are the ones that develop it. And yes, they can do amazing things. In fact, when we create what I will call designer materials, materials that can do anything we want, it's going to be because we can control their properties at the nano level that lets us do that. Absolutely. The chemists at NASA Langley are literally working at the benzene ring level with the material and modifying the basic molecular structure of the material to create the capability it wants. For example, we will say, this is a really good material, it flexes, etc., but we need a little bit more stiffness in one direction, so they will go down to the nano level and modify it at that level. So yes, it is huge. It is really, really huge what we can do there. I would say we've just begun, but the early results have shown a lot. The earlier example that I showed, we were doping in carbon nanotubes. Not huge pieces of material, but we were literally injecting nanotubes into those materials to get those capabilities. So yes, we have just begun to scratch the surface there, but our early results show huge performance improvements by being able to design at the nano level. Really quite a powerful technology. And it will likely be one of the biggest steps we make in the next century, without question. Yes, definitely. Really good question. I wanted to, by the way, just add something. A lot of students have asked me, how do they end up becoming an engineer? And for me, it started when I was 13. I did a book report on what it takes to be an aerospace engineer. And then I got my degrees from there. But for you guys to know, my family is from Trinidad and Tobago. I'm the parent of immigrants to the United States. My parents came over to the United States very poor, did their undergraduate degrees in the United States, and then voila, I came along. And so it's not that you have to come from this really wealthy US family. I didn't. Neither did my parents at all. And it was just a lot of hard work. My parents put themselves through school, working at minimum wage jobs in the US. And then, my brother and I both went to school. But most importantly was just really sticking at it with school. My undergraduate was really, really hard for me. Master's degree was actually easier, believe it or not. And getting a job at NASA was my dream, a crazy dream I thought could never actually happen, but it did. And I know many of you are looking at me like, wow, I could never do what she's doing, but that's not true. You could easily be coming back to Monterrey in 10 or so years to talk to other students that are doing work. And they will be looking at you like you're looking at me like, you're kidding. But it's really true. It's really true. A lot of dedication, a lot of hard work, but and being prepared is a big part of it. Many folks say it's luck, and that's not really true. The only way luck actually happens is if you are prepared to take advantage of the opportunity in front of you. My first NASA interview, I was almost unprepared for it, but I had a resume, a business suit, and interviewing skills all ready to go so I could go to the interview. So, even though it seems hard and some classes are incredibly boring, I had really sorry professors, but some are going to be really boring. Just stick it out, really. There are a lot of really, really cool opportunities. The other interesting thing is doing research at NASA. We have the opportunity to build and test. When I first thought of being a researcher, I said, oh, this is going to be kind of a boring career. I want to work with big airplanes and fly things for a living. But what I really didn't realize is that even as a researcher, you have the opportunity to dream, to build, to break, to flight test, to wind tunnel test, to stretch and turn and do all sorts of really cool things. And so having the opportunity to test things is really exciting, and to see your results coming through. So, research, when I was a student, I thought it would be a boring career, frankly. Everything I've just shown you is basic research, literally, at the very cutting edge. I showed you a couple of flight tests, but most of our research is done in the laboratory, really, with simple models. Start like this, and then get up to be wings, and then we take them. The guy that did this test, he literally found that airplane model in a closet someplace. We were done with it, and he took it out of the closet and put his little things on the back end of it to make it work, and dusted it off. So all of this is just basic research, and many of it's done by students that were just like you a few years ago. So research can be really exciting, more exciting than I ever expected earlier in my career. Any other questions?
Good afternoon. I'm Ramon Arriola. Have you started thinking about combining your ideas, like using this at the same time the materials, the piezoelectric materials with the stiff materials, so simulate the muscles and the bones, or combining the wing flaps, the feathers, with the air pumps to see how more control using both techniques?
Yes, and it is really hard, I gotta tell you. Yes, we would love to do that, and if you figure it out, call me. Yeah, it's really hard to do. Yes, in fact, feathers are so interesting. They're, you know, birds don't have big flaps, these little stupid feathers. You know, their wings are not smooth at all. They're bumpy, right, with feathers. They stretch them out and bring them in. And yeah, it would be great, yes. Nature does an amazing job of a very complicated, I mean, we looked at bird wings and, you know, hummingbird wings, unbelievable. They have the bones, the shoulder joint in a hummingbird wing. You know, our shoulders can only move really in a few directions. Those things can move all over the place. Their joint socket alone is amazing. And their ligaments can stretch far more than ours can. Really amazing. And they combine lightweight bones that are still stiff with skin and feathers. So yes, our dream would be to combine all of this, but it is so hard. We are not there yet. But we would love to be able to try something just like that. And we have tried many things that didn't end up working. And some of them, you know, taking a really flexible material and attaching it to a really stiff material, things just break, generally speaking. I've broken them myself, yes. So, yes, that would be perfect. And please call me if you figure that out. Because, in fact,